And before I do so, I have to acknowledge that I receive funding from the European Union to done. And today I will talk about my work on gravitational waves for primordial fluctuations. I will do some kind of intuitive overview of different possibilities. I will not touch the details. If you want to see the details, I invite you to check my review paper, or if it's not clear, then just write an email. So let me start, and I would like to show you some drawing. Let's check. Yes, I hope you can read it. I hope it's clear. This is the typical figure of an expanding universe. Time flows to your right, and then the universe, the scale of the universe increases, so it expands. But here I only focused on the early universe. And standard cosmology will start somewhere here with the Big Bang nucleosynthesis, and then we have the last catalytic surface, CMB photons decouple, and this is what we see today with the anisotropies. And so I put in green this part that we have directly explored with the CMB photons and Big Bang nucleosynthesis. Then from the CMB anisotropies, we have strong evidence that there was a period of inflation, and these anisotropies just approach the first few epochs of inflation. So we have strong evidence for that. We don't know how the universe started though, but we know it started very small, then inflated. And during this inflationary period, quantum fluctuations get stretched over the horizon, and this become the primordial fluctuations. This become the initial conditions for whatever happens afterwards. Now I mark in blue something that we have not explored directly. And what we do is just we extrapolate, so we know what happened here, we know what stuff happened here, so we extrapolate the standard cosmological model with the inflation. But in reality, we don't know. So mark this in blue. And this is where interesting physics can happen. And this period of time cannot be explored by photons, the universe was okay, but it can be explored maybe in the future and with gravitational waves. So I will be talking about gravitational waves on this unexplored early universe. Just as an example, I draw here, if one of these primordial fluctuations is very large, has a large amplitude, it will create some sound waves that they will generate gravitational waves. Or if it's very, very large, it can collapse and form primordial approach. So this is the main picture of my work. And now let's see a little bit more here. These are not the only sources, just let me, if somebody else is working on gravitational waves from the early universe, there are other sources here I classified with new physics during inflation. And this could be quantum fluctuations.
Yeah,
I don't know if, for security reasons, should we close or not? Much better for me at least. So one possibility is having quantum fluctuations over the tensor mode. Other additional sources during inflation can be gauge fields, action fields. Then after inflation, but before we have this Big Bang synthesis constraint, there could be some strong first order phase transition, cosmic strings that are sourcing gravitational wave, or there could be parametric resonances that are very rich possibilities. And let me show you some prototypical spectrum. So we hope that each kind of source or new physics has a different spectra, so we can distinguish them. This is not actually the case, but in the simplest case it is. So for example, cosmic strings, sorry, this is spectral density versus frequency. We have cosmic string, which is flat, phase order phase transition, which is a bump, induced gravitational wave, which is a sharp peak, and primordial gravitational waves, scale invariant. Here I show the sensitivity curve of future and current experiments, at least I would like to. But what I want to tell you with this figure is that So you just consider one frequency, and you take the scale corresponding to this frequency, and then you compute the temperature that the universe had when it had that size. For 10 to the minus 9 hertz, it's 180. And then for probably 200 hertz, it's 10 to the 10 G. So this gravitational wave observation will probe big chunk in the unknown period of the universe. So if there was some loud signal of gravitational waves, we should see. Oh, here I wrote some disclaimer. These spectrums are all derived assuming radiation domination. I'm assuming the extrapolation of the standard cosmological model. If you change that, then they will change. So this is the overview of my talk. First, I will review a bit of these induced gravitational waves, how you can estimate the amplitude and how they are generated. And then I will do it in the simplest standard cosmology case. Then we see what happens if we go beyond that into examples. One is I will change the expansion history of the early universe. So it means it's not dominated by radiation, but something else. And the other one is I will change the typical initial conditions that are assumed. So people just take adiabatic initial conditions because from CMB observations we have no evidence for isocurvature. But on that scale, on very small scales, we don't know. So I will see what happens if I consider another type of initial condition. So let's start with the review. Perhaps you don't know this, so let me tell you, it's curious. The first one to notice this effect was Guillem Domènech a long time ago. He said gravitational waves can be induced by density perturbations, even if you don't have tensor perturbations to begin with. So he was the first, and then Matarese rediscovered this without knowing the word automata. And other important works are those people in Cosmos, 2006, and Bauman, Steinhardt in 2007. But it wasn't until 2008 that Saito and Yokoyama made the connection between primordial black holes and induced gravitational waves. Then this topic was kind of silent until there was the first LIGO detection. People thought maybe it's primordial black holes and they can be all of dark matter and so on. And then people started to study more induced gravitational waves. At least some of these references. Okay. So let me take some more rigorous picture of what's going on. To do that, I draw some diagram. Here you have a physical scale, logarithm of physical scale. For example, the current Hubble radius, so the size of the universe now. In terms of the default, so logarithm of scale factor. So here you have today, and the beginning we have inflation. And with this CMB observation, we can probe the speed of inflation and Planck satellite has a nice constraint on the primordial spectrum, so it's almost scaling back. But these observations probe until some points, at just maybe the first 7 equals, and then we don't know what happened. So, for example, the inflation was not just this low roll inflation, but at some point there was some turn in the inflationary trajectory, some ultra slow roll phase, some new physics that enhance the primordial spectrum. And here I just draw a peak because it's the simplest to study. So there could be a peak with an amplitude much larger. So you have fluctuations on small scale that have a large variance. Then this goes as usual. They leave the horizon, they freeze until they enter the horizon again during radiation domination. We don't know how inflation ends. Let's assume it ends quickly. This does not affect this mode that after the horizon. Then this fluctuations will enter the horizon, and we'll have some interesting physics. So now let me a little bit draw what happens here. So consider you have a peak in the primordial spectrum at some given scale K star. So this means that you have fluctuations on some scale K star or lambda star that are drawn, the amplitudes that are drawn from a Gaussian probability kinds of fluctuation. And I will assume this variance is fairly large. Yeah. And initially, the fluctuations are super horizon, so they don't evolve. And at some point, the horizon size will be comparable to the fluctuation size, and they will start to evolve. And now two things will happen. One is that if the amplitude of fluctuation on the tangent horizon is large enough, so it's above some threshold, it will collapse to a primordial black hole. And this black hole will have a mass proportional to the mass inside the horizon. And you can relate the mass with the size of the horizon and the size of the fluctuation. So we know what is the mass of the primordial black hole, more or less. Now, in more general terms, not just looking at one patch, we will have these oscillations. If they are not too large so that they collapse, they will start to oscillate, so they will start to create waves in the fluid. This is what I try to illustrate here. And this will create some oscillations in the metric fluctuations, which are these kind of gravitational waves. Now, the frequency of these waves, the typical frequency, so the peak frequency, if you want, can be related to the typical frequency of the oscillation, in this case that. So with this simple picture, you can see that the mass of the primordial black hole and the frequency, peak frequency of the gravitational waves are related to each other. Now, how big can these waves be? At first order, this tensor mode of gravitational waves is just a free wave propagated in an expanding universe. So nothing happens there. Second order in cosmological perturbation theory, a source term will pop up. And this source term is proportional to the probability perturbation square, or the gravitational potential, if you want. So now with this, looking at this, you can have a rough estimation of the amplitude of this tensor mode. Very quickly, you take, so this is the square of this capital phi, so the power spectrum is the square of 8. So you will have the square of the power spectrum of the probability perturbation times some redshift factor, that here I related to the density ratio of radiation today. And if you put some numbers, you get this 10 to minus 6 power spectrum square on scales much smaller than the CMB. So to see when this becomes important, and I show you this figure. So here you have spectral density versus frequency. If you take the CMB primordial spectrum of fluctuations, you will get some induced gravitational background, which is below this, so you will not see it. But if you start increasing, and you get maybe 10 to minus 4, I think you start to see it when it's 10 to minus 5. But if the primordial spectrum says less than 10 to minus 4, you should see it maybe in pulsar timing arrays on the side. And if it's even larger, 10 to minus 2, not only you will see it on all of the detectors, or with a big one detector, but it will also have detectable primordial black hole quantity. So this is the interesting aspect of these gravitational waves, these induced gravitational waves. You may have some detectable primordial black hole counterparts. You have two observables that are related.
What do you mean by detectable primordial black hole? What does that mean?
With enough fraction. I mean, fraction 10 to minus 3 or something. Maybe in the future you'll see it. That's what I mean. Some, let's say the fraction of black holes is not negligible. As you probably know, the fraction of primordial holes go exponentially with the inverse of the power spectrum. It's very large.
Right. So the word detectable, what does it mean?
Detectable means that you have enough primordial black holes that you can see them. Obviously not now because we have seen them, but maybe in the future by micro lensing or something like that. Or if they are dark matter, you would see the effect of dark matter. So talking about primordial black holes, I draw some, maybe it's a confusing connection, but let me explain. So you can connect the mass of the primordial black holes with the frequency of gravitational waves. So here in the top part, I show you some interesting ranges, maybe 10 and 10 hundredths solar masses of primordial black holes, which could be related to some of the populations of LIGO. You have a planet mass of primordial black holes, which could explain some of the microlensing events seen by Ogle. And maybe you have asteroid mass primordial black holes, which are 100% black matter, or maybe very, very tiny black holes which evaporated in the early universe and repeated. So this, for example, this black lines means measure. You will see the measure here of LIGO. And these straight lines means the connection with the induced gravitational wave. So for example, if you have 100 solar masses, you will see it in pulsar timing array. If you have asteroid mass primordial hole, you will see it in light. But this is assuming radiation-dominated universe. If you change that, so if you don't know what is the early universe expansion history, then the connections change a little bit. And one interesting example that I want to tell you is that, so if you take this possible background seen by nanograph on the International Pulsar Timing Array, if you consider an early matter-dominated phase, the connection of this gravitational wave is planet mass and primordial black holes. So that is a large change if you change the expansion. Here I show you what is the relation in radiation. Okay, I think so. This is the end of this review of induced gravitational waves. If you have any question, tell me now. Now I will go to modifying the expansion history.
Question.
Yeah.
What is asteroid mass? You have redshift or what?
Lisa sees the induced gravitational wave of this. Well, when you compute, of course, the frequency is redshifted. But when you compute the relation with what I showed you, the mass and the frequency in radiation domination. So asteroid mass, what is it, 10 to minus 16 solar masses or something. I think that is not yet at the level.
Actually, sorry.
Yeah.
Really, but you're talking about wave generated on what?
By the primordial fluctuation.
When you created this structure?
When I create?
When you created this primordial?
Primordial black holes, yes. So actually this induced gravitational wave generation happens at horizon crossing. Primordial black hole, I mean, starts to collapse at horizon crossing, but it's not at exactly the same time, but yes, probably there. So but primordial black hole is a rare event, so not all patches will collapse to primordial black hole. And those who does not collapse, they will oscillate and generate large waves. So these two things happen at the same time of the universe.
So for the primordial black hole formation, are you assuming something like the root conjecture or?
This I don't know because I'm not an expert in this part. So what people does is that if you just look at one patch, I'm not sure in numerical simulation what they do. But when you look at one patch and you look at this large fluctuation, it is a closed universe. So that's why you can estimate the mass of the black hole. All of these closed universes collapse. Nothing to do with the typical collapse of a star. So everything that goes there just collapses.
No, I think it's similar. But to calculate the amplitude of this, you need to assume something about how they're induced.
Why?
So if I take, well, let's take standard collapse.
Yes.
Right? Spherical is
Okay.
collapse generates.
So
what exactly are we doing?
So it's not the gravitational waves from the collapse of the fluctuation. So this is just cosmological perturbation theory expanded at second order.
Yeah, I'm trying to understand what's the connection. Yeah, sorry.
So it's these fluctuations of the.
But what's the connection then with these objects, with the formation of primordial objects?
Well, let's say the relation is that they are generated by the same primordial fluctuation. So primordial fluctuations, some of them are large enough to collapse. Those that are not, they generate waves.
So yes, you were saying that when you solve the structure at the same time, it does minus waves by time that you generate the waves.
Right. So okay. So primordial black holes, I just talked about one Hubble patch, but they are rare. So they not every patch will form primordial black hole.
Okay.
So very rarely one of these guys will collapse. In general, what happens is that you have huge waves that are generating gravitational waves.
I think what you form the object also as a byproduct or at the same time.
It's at the same time. So there will be oscillations and there will be some Hubble patch. But this is very large. It's not connected to the process, but they are generated by the same seed.
Okay.
Okay. So let me move on. How am I going this time? More or less.
20 minutes.
Okay. So let's see what happens. Now what I have in mind is this figure. Again, you have physical scale and logarithmic scale factor of inflation, but then inflation ends and you enter some period which is not radiation. Matter domination maybe, or kinetic domination of stiff fluid. This is the equation of state. And then you have again some peak somewhere that leave the horizons and enter at different points depending on the expansion. So this is what I call this heating phase that I don't know. And then at some point we enter the radiation dominant phase. Here just as an example, I consider heating temperature to the 4G. You can be as low as 10 MeV or something like that. This could be really So if you look again at the equations of motion, you will see the effect of having different expansion history, obviously different friction. But another important effect is that you will also change the evolution of the scalar fluctuations. So these are two effects. The third one is that you have here, this is an harmonic oscillator, and this will oscillate, so this is a periodic force. And there can be resonances when you have an oscillating force to an harmonic oscillator. This will happen with the wave number of the tensor mode is 2 times the wave number of the scalar mode times the sound speed of the. So let me just show you what happens with examples. The first one is the simplest for me. It's not Dirac delta, it's a broken power law. And I will consider this. This is a logarithm of primordial spectrum versus wave number. And I assume I have one broken power law. Infrared tail with some spectral index NIR, and UV tail with spectral index NUV. And this is usually what happens in single field inflation models. So we have something like this. This NIR is usually 4, not much larger than 4. And NUV is related to the second derivative of the infraton potential. Here I said you can also relate it to non-Gaussianity or to the. Now what happens if I compute the induced gravitational waves? So you get another broken power law. This time you have infrared tail that goes straight to the cube. And this is some kind of universal IR slope that is shown here. And then you have a UV tail that goes to this minus capital delta, and you have here the value related to NUV, but depending on the value of NUV, you have different possibilities. So of course, if you see this UV tail in the future, you can say, oh, I can give you some information on the physics of inflation, of the second derivative on INFN. But now let's generalize it, and let's consider some arbitrary equation of state, which I call W not equal to 1/3. This is what you get. So you get a double broken power law with some mid infrared tail that depends on parameter CTP and I give you. And you see here there's another scale, which is the repeating scale, below which you get the radiation domination and you recover the universal. So now it will be not so easy if you just see the UV slope. how would you tell what is NUV and what is the expansion history? Of course, if you see everything, then probably you can tell them apart. But if you only see one part, it can be degeneracy. This is just you can derive it assuming some causal physics. You have a localized event, that generates the gravitational waves sometime, and these modes are super horizon modes at that time. So it doesn't take much time. If you compute it all with 5, to just verifying causality, you get the code. If you have Dirac delta, I will show you now. Any questions in this example? Then I will go to the second example, which is a very sharp peak. I will consider Dirac delta. And two cases. I will have a perfect fluid and a canonical scalar field. So this is the spectral density, that's a wave number now, normalized to the peak. If you take a perfect fluid, you see there's a big peak, sharp peak, which is the resonance I was telling you about before at this position. So when you increase the equation of state, the fluid is stiffer, then the resonance moves to the right. Now, if you have a canonical scalar field, for example, you have that the fluctuations provide at the speed of light, and this resonance is forbidden by conservation of momentum. And then there is no. So this effect is on top of the one I showed you before. So you will have a different mid-infrared slope, and you will get to the escape cube.
Sorry, actually, I didn't understand you. This is a parametric.
The parametric resonance.
Yeah. So what is the difference? Can you explain again why?
In this and this?
Yeah.
This is the non-specific one. So I just see that the resonance you're pushing it. I didn't explain. So there's a cutoff due to momentum conservation. So you cannot in a dispenser mode, which are equal to the sum of the scalar modes. Okay. So you have a cutoff. Yeah. When you increase the sound speed to 1, you just put the resonance in the forbidden band. Okay, so please remember, here you have a peak, here you don't, because now I will show you one example, but it's a bit more complicated. So is that if you have large oscillatory modulations in the primordial spectrum. So I will take as initial conditions this spectrum, which has order 1 oscillations. And if you want to know the details of how you get this demonstration, I invite you to read the paper that people in Paris. It's a very sharp turn in the inflationary trajectory, and you get all one. Now, what do you think the spectrum will look like if I consider a perfect fluid with this radiation or a canonical scalar field that at the background behaves as radiation? So naively, what I thought is that if you have so large oscillations, and you should see oscillations all the time, but the guys in Paris, that they are very smart, they told me that this is not the case. And this is because this is a second order effect. So you are integrating over the square of this power spectrum. So this integration over the square, you are just averaging out the oscillations. So this is what happens. Also, when you go to the previous one, canonical scalar field sound speed equal to unity, you don't see the oscillation. Everything is averaged out. There is no resonance. Now, when you have a perfect fluid and there are resonances, what happens here is a source term, which is, you can sort of imagine this is kind of a comb of delta, very, very sharp. You have a sum of comb of delta to the square. So you will have a sum of oscillations that are resonating with HHA. So it's this resonance that appears here. This oscillation disappears because of the resonance, and therefore the frequency of the oscillations in the gravitational waves is related to the primordial oscillation by a factor of 6. So now what does this mean? This means that if now let me just change a little bit this figure. Now I consider some stiff fluid. Okay. Now, in the case of stiff fluid, the frequency of the gravitational wave oscillations are much higher, and the amplitude is also larger because the resonance was very sharp. And one interesting thing we found is that it's not a general statement. We studied as many examples as we could about this. And in radiation domination, we could not find an example with an amplitude larger than 20% of the envelope. So, but instead, if you consider stiff fluid, the amplitude can be above that 20%, can be 40% or so. So if we ever find this kind of spectrum with large oscillation, and the amplitude is larger than 20%, this means not only you have oscillation in the primordial spectrum, but you have some non-trivial expansion. So that's what I wanted to tell you about these different expansion histories. If you want to ask me more about this, do it now, otherwise I will go to the other initial conditions. All right, so what happens, before I assume adiabatic, I didn't say it, but sorry, it was curvature fluctuation. Now what happens if we change that and we take isocurvature fluctuations on small scales? I'm not sure if you're familiar with how isocurvature goes. Just let me briefly tell you how it evolves. We have some intuition. And I will consider two examples at the same time, which are just, they behave the same. One case I will study is just color matter fluctuations. So you have, I will assume I start with a homogeneous universe with radiation and some fluctuations in dark matter on small scales. But this could also be due to a primordial black hole. So when these primordial fluctuations collapse to primordial black holes, these things are scattered around the universe. And what happens is that they are creating inhomogeneities. So if you look at some coarse grain scale, these primordial black holes behave like a perfect fluid with some density fluctuations. And this is what I try to illustrate here. And now in this perfect fluid picture, both cases, the primordial black holes and cold dark matter will behave the same. So let me take now one time step, and maybe I should say that this primordial black hole density fluctuation was first noticed by Papanikolaou and Blanc, and then we later studied the induced gravitational waves. So let me take one time step. Now so radiation decays as 8 to the minus 4, but matter decays at 8 to the minus 3. So the relative weight of matter increases. So now we have more energy density in the matter, and it starts to induce some small fluctuations in the radiation fluid, which here I just said it's just a small induced adiabatic perturbations. And these adiabatic perturbations then they will follow the standard procedure and create induced gravitational waves. So this is what will happen when I consider a gravitational wave by cold dark matter isocurvature. But I don't want isocurvature to be so large on scales that enter the horizon after equality. So everything happens during radiation domination. So this will be important. Also, you can see that the later a mode enters the horizon, the larger is the transfer. So if it enters earlier, so there will be not so much transfer, but if it enters later, the relative weight is larger. Now, what happens if matter dominates the universe? Then all this initial isocurvature becomes adiabatic fluctuations. I illustrate this here, and then they induce gravitational waves. This is the important component when you have primordial black holes. So for the second possibility, I will assume that these primordial black holes dominate the universe, and then they evaporate, and they generate a lot of gravitational waves. One interesting point is that assumed by Hinamata, if you have these gravitational waves induced in an early matter era, they get enhanced if the heating is sudden. And this is exactly like primordial for evaporation. I will come back to this point later. So let's look at the first example, and gravitational waves by cold dark matter isocurvature. Here I wanted to show you in more detail what happens to the fluctuations, the scalar fluctuation. So this, you have transfer functions with time, curvature perturbation, isocurvature that subtracted the initial amplitude, and relative velocity. So you see the curvature perturbation increases and when enters the horizon it decreases. The isocurvature fluctuation subtracted the initial amplitude and grows, and when it enters the horizon, keep growing. This means that at some point, this isocurvature will be very large. It will hit some nonlinear regime, and will form primordial records. I will not touch this topic here. You can check the paper by Samuel and myself. Here I will be concerned about the generation of induced gravitational wave, which happens much before you get the nonlinear regime. It happens at horizon crossing. After that, curvature perturbation decays, and it's not so important what happens. So the spectrum we get, you can see, maybe let's start here. This is the, I consider Dirac delta here, or Dirac or not normal peak, not very sharp, but sharp peak in the primordial isocurvature spectrum. This is the amplitude versus the peak wave number. And you can see this is the parameter space that we can probe with future gravitational wave detectors. The amplitude of the fluctuation is very large, but it's the only way you can constrain or test this parameter space. On small scale, this is the only way to test. We have derived all the analytical formulation in this paper for the gravitational waves, and if you put a Dirac delta peak, you get this. And the red line is the adiabatic fluctuation that I showed you before, and the blue line is the isocurvature. They look similar, but not quite. Or maybe if you can see the whole spectrum, you can tell them apart. Now, some problems here about, I cannot see your face, but I don't know what face you may want to see these numbers here. So there is one small caveat here, but it's actually complicated. So to generate this large gravitational wave with large isocurvature. But if you look at the definition of isocurvature, you see that you need most of the regions of the universe to be almost empty, so that you can have large states of fluctuation. You need a distribution that is not Gaussian at all. It's highly skewed with a very long tail. So you cannot use the usual estimates of Gaussian perturbation. That's the problem. Now here we did some heuristic estimates by considering some chi-square, and we found that the induced gravitational waves are related to the 4-point function of fluctuation. So if you have a large tail, you have a boost of the amplitude of gravitational wave. So some heuristic estimates gave us this boost in the amplitude. So this would be the parameter space, and we hopefully can prove. But this is an open issue. Oh, okay. That's fine. So let me go to the last possibility, gravitational wave by primordial whole density fluctuations. So this is what's happening in the early universe. Here you see the logarithm of density ratios. Blue is primordial black holes, red is radiation with defaults. So initially primordial black holes are completely subdominant, but eventually they dominate the universe, and then they suddenly evaporate and radiation dominates. And this happens with less than 1/4 of default. It's something very fast. Just everything explodes. This is because I consider a monochromatic primordial black hole mass function. If you have a broad thing, it's softer. But for simplicity, I use this monochromatic. So you have a very sudden evaporation. And the induced gravitational waves are generated by the, now I wrote the velocity fluctuation in the radiation fluid. So this sudden evaporation will create huge waves everywhere and have a huge amplitude of the induced gravitational waves. If you want to know more details, I recommend you look at the paper by Nomata. it tells more details of what's happening there. Now, this is the spectrum that we get from this sudden transition. This is the spectral density of gravitational waves. So frequency, we have a very sharp peak. The position of the peak depends on the mass of the primordial black hole. And using this spectrum, we can already put constraints on the initial fraction of primordial black holes. This is what I did here. So the lower bound is the initial fraction versus mass of the primordial black hole. The lower bound in red is the minimum value you need to get primordial black hole domination. If you are below this, primordial black holes never dominate. The upper one is by requiring that you don't touch BBN constraints, current BBN constraints. This is the blue line. So with our estimate, we can reduce the initial fraction of primordial black holes to maybe 2-3 orders of magnitude. There's some interesting possibility too, that if these primordial black holes, for some reason, they spin very, very large. And you will also see them in the effective number of relatively big species in the CMB. Yes, okay, so this is a good question. I don't have a very good explanation. So what I can tell you, this peak is related to the resonance. So when you compute the spectrum of gravitational waves, I have to split the two. So one near the resonance and the other in general. So you get these two contributions, one broad spectrum and the peak for the resonance. And then when you sum, you have just a proper formula. So the peak is because of the resonance. But so there's some problems too here. For future work, that when you look at the density fluctuations that are generated by these primordial black holes, there's a moment during this primordial black hole domination that they enter the nonlinear regime. They are all within this range, so they can be very large. And so, not so clear what happens. Probably what it means is that black holes merge and so on. And we cannot treat it with linear perturbation. But in any case, this production of gravitational wave will not stop because some black holes merge, and we still have the curvature perturbation on large scales very small. So this estimate we gave using linear perturbation should be giving you an order of magnitude estimate. Now, if you want to be precise, then we need to do some numerical computation. One possibility is that maybe generates turbulences, but this is just a speculation. So I guess, is it okay if I finish now?
Yeah, take a few minutes if you want, otherwise.
So let me just put my slide summary, and I hope I convinced you and you understand a little bit of what's going on. And showed you that in these gravitational waves with this primordial black hole counterpart, you can use them to probe not only the physics of inflation by seeing what is the primordial spectrum of initial conditions, but also you can test the physics after inflation by the equation of state of the universe, the different sound speed of fluctuation, or maybe a primordial black hole dominated universe. Thank you. I will stop here.
Thanks very much for the nice talk and very well timed as well. Do we have questions?
Can you say a few more words about how the black hole evaporation is generated?
The waves?
Yeah.
Yes, okay. Let's see. Can I go back? Yes. First thing, we are using linear perturbation theory. So this is why I'm not sure if it's 100% correct. But if you trust linear perturbation theory, explained at second order, you see the velocity potential is proportional to the derivative of the gravitational potential of curvature perturbation. What happens in matter domination, this is constant. So you're going to obtain constant gravitational potential, constant velocities, and then suddenly, with a step, and the derivative of this potential is very large.
So how exactly are you calculating? So you assume that all black holes evaporate at the
Right.
same
So
time?
then I'm using this perfect fluid approximation. So I treat all the primordial black holes are perfect fluid, and then I see these fluctuations of this perfect fluid that are valid in scales much larger than the mean separation of primordial black holes. So we are not looking at small scales where you would see the structure, just very large scales, much larger than the mean separation.
I see. So the evaporation just heats up this fluid
Yes,
on scale much larger than.
yes, that's what happens. But it will be interesting to know exactly what is going on at the small scale. It's complicated. Yes.
You mentioned that this kind of model can change the equational state of, let's say, for the universe. Can you control that, or how you can test the model? That's a big question, right?
Well, right.
You can, like we say, you can reject of them, or you can, well, elaborate on.
Right. So you have two ingredients here. One is the amplitude of the primordial fluctuation, and the other is the equation of state. Now you need an amplitude which is larger than CMB. So I don't know if you assume CMB and then you assume, for example, if you have a stiff equation of state, these tensor modes with a blue tilt, so maybe you hit some constraints, but probably the ones from just linear perturbation will hit the bound before. I don't know. So maybe I should, let me show you the spectrum. Yes, here, yes. So here, what we are probing is whatever happened after this scale entered the horizon. So something before that, you don't see. Okay, but you are only probing since this mode entered the horizon until it appears. Okay, that's what you're testing. And so maybe with a combination of two, you can constrain the amplitude of the spectrum in terms of the equation of state, or something like that. It's interesting. I didn't do it yet, but okay.
Any more questions? Well, if I may ask one, very naive because I'm not an expert on this at all. You mentioned at some point that you may have to rely on some numerical simulations for understanding something.
Yes.
What numerics do you use in this type of research?
This just analytics as much as possible, and then the numeric is just simple integration. So I didn't show you here, but if you look at if you look at the equations of motion, you go to Fourier space, you get an integral over the internal scalar momentum, and if you cannot do this analytically, you do numerics, but it's something so.
Okay.
For the numerical things, I was thinking about this primordial whole universe, the dominated universe, and then you need n-body or something like that.
Okay, for simulation. Thank you. Any more questions? If not, let's thank our speaker again.
If you enjoyed the video, like and subscribe.